So in this segment, we're going to be looking at a very small and simple topic, which is the wave-particle duality. What does it say? Any object in the real world which you take has two natures or two characteristics. You can think of it like a split personality thing. So it has the wave nature as well as the particle nature. And both of these characteristics do not exist at the same time, as in a particle does not exhibit properties of both these natures at the same time. There are certain situations in which a particle behaves like a wave and an object behaves like a wave, and certain situations in which it behaves like a particle. So if you remember from your 12th standard physics, we start by studying ray optics, meaning we first learn to think of light as a ray, and in that sense we study reflection, refraction, we draw ray diagrams and all that. But then we move on to these concepts like interference and diffraction, and there we start looking at light as a wave of particles. So and then we come to the conclusion that light is both a ray as well as a wave, but it does not behave like a ray and a wave at the same time. So when you're dealing with a phenomena like reflection and refraction, it behaves like a ray. When we're dealing with diffraction, interference and so on, it behaves like a wave. So depending upon the context, it shows a different nature. So we studied that with respect to light, and what de Broglie's hypothesis states is that the same idea is applicable to any entity, any object you look at in the real world, ranging from microscopic objects to big the things we use in our everyday life, macroscopic things. So according to de Broglie's hypothesis, any particle of mass m moving with a velocity v can be associated with a wave. And we all know this famous equation, E equals mc square. Einstein gave it. What are the terms here? E is the energy exhibited by the object, m is its mass, and c refers to the speed of light. Or here you can replace c by v, where v is the velocity with which the object moves. And we also know another equation for energy, which is h nu, and nu is nothing but c by lambda. So this is also an expression for energy, this is also an expression for energy. So we equate both, mc squared equals hc by lambda. And this comes from the particle nature. A particle has a mass and a velocity, and this comes from the wave nature. A wave has a frequency and wavelength, and by equating both these, we are trying to imply that the same object has a wave nature as well as a particle nature. So when we equate, one c term on either side will get cut. So you have mc equals h by lambda, or lambda equals h by mc, which is h by p. This lambda is called the de Broglie wavelength. And what is p? P is momentum, the product of mass and velocity. So what is Mr. de Broglie trying to tell us here? The basic idea is that any object you take, it has a wave nature and a particle nature, and there are certain situations in which each respective nature and the properties are exhibited. We'll not be going into too much detail in that, but we'll touch upon that in one of the future slides. But the idea is every object in the real world possesses both wave characteristics as well as particle characteristics. So by equating the energy of the object, because it's the same object, ultimately it has only one energy value. You have two expressions for the same energy, one in terms of the particle nature, one in terms of the wave nature. By equating both and then cancelling common terms and bringing the numerator, denominator, and doing some basic mathematical operations, we get the expression for the de Broglie wavelength as h by p, where h is your Planck's constant and p is momentum.